Good afternoon, I'm Wutran. Today I'm going to present DeepLight, a project on screen camera communication. There is a joint work with Gihan Jayatilakar, Professor Ashwin Ashok, and Professor Archana Misra. So, what is actually screen camera communication? For example, we have a message to transmit, so we will embed it into video frames displayed on the screen. A user then uses a camera, for example a smartphone, to record the video. And from the recorded video, it decodes and extracts the original message. So there are many use cases of screen camera communication. For example, we don't want to show too much detailed information on an advertisement on a screen because it distracts the users. So we can transmit the detailed information through screen camera communication. If a user is interested, she can use the smartphone to decode and see the detailed information such as allergy advices, calories information. You can also use screen camera communication to transmit commentary voice to a user. So only the user who uses a camera, for example, in a pair of smart glasses, to decode the audio will hear the voice via the earbuds, and it won't annoy others who are not interested in the game. So the first key objective of screen camera communication is to preserve the visual quality, because we don't want the user to feel uncomfortable when watching the video. And the second objective is to achieve high throughput, because we need to transmit data to the device. Now, let's see how screen camera communication has been done before. At the encoder side, we could use frequency modulation to embed the data, but Manchester coding is more common in previous works. Assume we have some data, we arrange them into grids. From each grid, we generate two complementary modulation frames. A value of 0 becomes plus delta and then minus delta, and a value of 1 becomes minus delta then plus delta. These modulation frames will be added to the video frames and shown on a display at fs frame per second. Because of the modulation, each cell generates flickers. The flicker frequency can be half the display rate or 1/4 the display rate. To reduce the flicker perception, previous works rely on very high display rate. It is known that human eyes cannot perceive flickers if the frequency is higher than a threshold, around 50 Hz, and can be as high as 70 Hz. Previously, we know that the modulation can create flickers with a frequency of a half or 1/4 the display rate. So to achieve imperceptibility, we need a display rate of at least 100 frames per second for invariant data and 200 frames per second for variant data. And the key question is how to achieve imperceptibility at common frame rates, for example, 30 or 60 frames per second. At the decoder side, previous works decode the data in a grid splitting manner. Assume that is the original encoded screen. The decoder first detects the screen and split it into a grid similar to the encoder grid, but under real-world peak condition, for example, hand motion, artifacts, or the textures in the scene. It easily includes some errors, for example, mistakenly include the border of the screen. Now, let's zoom in at a cell near the border. It shows a big mismatch between the transmitter cell and the receiver cell, and thus cause severe interference. So the big question is how to support robust decoding with imperfect screen extraction. By solving these two problems, DeepLight makes the following contribution. We propose and evaluate a blue channel modulation for imperceptibility at common frame rate, as well as a learning-based holistic decoding method that is robust against imperfect screen extraction. We also developed a hybrid screen extraction method for practically high accuracy. First, how DeepLight achieves imperceptibility at common frame rate. So human eyes are known to be less sensitive to blue light. So we conduct an experiment to validate this effect and to see if it is better to use the blue channel for modulation. We asked 11 participants to watch and rate video quality modulated on different channels. Please note that blue brightness channel was commonly used in previous works. However, the green and blindness channels achieve very low scores, even at the least amplitude. So we need to avoid these channels. The red channel is only good with the least amplitude. And as expected, the blue channel is much better and seems to be the right one. But the blue channel has its own problem. For example, there's the iPhone X gain setting at normal light, white light. It means that the camera needs to set the highest gain for the blue channel and thus cause more noise. And previously, we knew that we have to deal with the cross-cell noise also. So should we increase the delta to cope with noise? The answer is that we can't increase it too much, as it decreases the visual quality. We propose to use a learning-based decoding mechanism instead of hard resolving to deal with sensor noise, and to avoid grid splitting to deal with the cross-cell noise. The question is how to do that. So we propose a holistic decoding mechanism based on a convolutional neural network. So why? First, it can learn the temporal relation, which is the Manchester coding. Let's look at the input. We stack 3 consecutive blue frames, so it can learn the Manchester coding from a positive frame, a transition frame, and a negative frame without hard coding any threshold. And actually, it is temporal spatial relation. Second, each output bit is inferred from the entire input image, not just one cell. So we don't need grid splitting at all. So now, what if the input stack is these 3 frames? Of course, there are many invalid frame stacks that does not contain a positive frame, a transitional frame, and a negative frame of a same Manchester pair. So we need to filter out those samples. We use a frame structure include Reed-Solomon coding, a checksum, and a sequence number, and then detect the invalid sample in a cascading manner. A frame is considered valid only if it passes all of these checkpoints. Okay, so till this point, we know how to encode the data into blue channel and video frames. We also know how to decode the bits from an extracted screen. But the camera frame includes a lot of non-screen pixels. So how can we extract the screen? Of course, we could use the classical canny and half transform, but it is easily tricked by line textures near the screen or even in the screen content. So the extracted screen in reality usually includes a lot of non-screen pixels and exclude a lot of screen pixels. We propose a hybrid method for screen detection. First, the system applies a unit to segment or filter out the non-screen pixels. Then it analyzes the contour of the segmented image to detect the 4 edges of the screen. Then extract the screen area. Of course, this is not perfect, but okay for the DeepLight holistic decoder. So now we have everything we need for a screen camera communication system. Before going to the evaluation of DeepLight, I want to define some performance metrics. We use mean opinion score to measure the visual quality of modulated videos. A score of 1 means very unpleasant, and a score of 5 means it is as good as the original video. And the raw throughput count all the bits that match the transmitted bits. And the throughput counts only the recoverable bits. And goodput counts only the useful recoverable bits. And note that the raw throughput is not useful if bit error rate is high. Just imagine if a random guess, the bit error rate would be 50%, but it is unlikely to be corrected. And in our experiment, we use a 25-inch Full HD monitor with a refresh rate of 60 frames per second. The camera records Full HD video at 120 frames per second, and by default we use a grid size of 10 by 10. First, we evaluate the visual quality of the modulated videos. We recruited 17 participants. Each watched 6 videos with 4 different encoding techniques, including original or no encoding, are encoded with different techniques, including DeepLight, highlight, and chroma code. So DeepLight outperforms others and achieves a score close to the original video. In terms of performance, with 0% of screen extraction error, it achieves a good output of more than a kilobit per second, even at a viewing distance of 2 meters. And when we increase the percentage of extraction error, it is robust up to an error of 30% of a cell size. At an error of 40% of a cell size, it suffers a lot from shift error. And DeepLight can scale up with larger grid size also. The basic model decodes a 10x10 grid, so we can just apply the basic model repeatedly over the input. So at a grid size of 30x30, it achieves a throughput of about 26 kilobits per second with a good output of about 4.7 kilobits per second at a viewing distance of 1 meter. At 1.5 meter, the cells appear too small in a camera frame, so the output is significantly lower. But I believe the higher resolution video might help. We also conduct experiments with handheld camera with real persons. We recruited 7 persons. Each time a person sits on a chair at different distances, we intentionally ask them not to rest their arms on the chair arms to record natural hand motion artifacts. For most of the participants, the system achieved higher than 0.9 kilobits per second, even at a viewing distance of 1.9 meter. For P7, the performance is much lower as he has a severe hand tremor. Next, we evaluate DeepLight on a smartphone. First, we examine the processing time of each component. Clearly, the screen detection is a bottleneck. However, we don't need to run the screen detection for every frame because the screen won't change its position in the camera frame significantly in a short period of time. We then test how the frame error rate increases if the screen detection is executed intermittently, this time with a walking user to include more motion artifacts. So the sweet spot is at an interval of around 300 milliseconds, and the system can support around 60 frames per second. And this is a mobile phone prototype of DeepLight. So every time the user presses the button, it will decode the data in the latest 32 frames and show the result on the phone screen. To compare with previous works, in terms of visual quality, we implement the encoder based on the description in the previous papers and conduct user studies. In terms of performance, we refer to the reported values in the previous papers and normalized it to 60 frames per second. DeepLight outperforms others in terms of visual quality and throughput and good output. In terms of processing time, though DeepLight does not achieve such a low processing time as highlight, it still supports around 60 frames per second processing on a mobile phone. To summarize, in this project, we show that using only blue channel for modulation can reduce the flicker perception significantly, and so achieve almost imperceptibility. By using a unit-based segmentation before applying classic contour analysis, DeepLight can detect screen accurately. And we show that a convolutional neural network can decode data robustly, even with imperfect screen extraction. Finally, DeepLight is robust enough to support handheld camera and mobile execution. Thank you.